Yes.
Yes.
All
Okay, I
good.
don't hear a word, but okay. So, I mean, I will first apologize for this talk, which is completely far from the topics of this conference. I have an incredibly good memory of Grégoire, and Anne and Claude say so incredible words about. I mean, he was a friend. He cared about people. Just to give you an example of this, is in the 14th July 2016, we have a terrorist attack in Nice, and the morning after, I get the mail from Grégoire. And I don't perhaps need to translate. I mean, I hope you are well, and after these terrible events in Nice, and so this is one of the aspects of Grégoire. I mean, Grégoire was an incredible good scientist, but he cared about people, and Claude and Anne say that very well. So let now me go to my talk. So something is wrong here, but it's okay. So my talk will be found very strange, but this is a project that I start almost 10 years ago with Enrique Tirapegui, and which is related to use history to teach physics, elementary physics. I mean, physics from college in France and lycée, and perhaps the first year university. I have made a lot of experiments in all this teaching. Basically, the idea, and probably everything starts from the interest that Yves Pommeau and I had for Newton. So we start a long time ago with Yves to read Newton Principia, and of course, as many.
I'm not sure we see what you want us to see. We are still seeing the letter of Grégoire, the email of Grégoire.
Yes, this is yeah. Okay. So the idea was, I mean, with Yves, we start to read Newton Principia, and of course, as many realize that Newton don't write a single equation in the Principia, at least book one. It was just geometry, Euclidean and Apollonian geometry. So then we become a little bit crazy to try to understand this and realize that Maxwell, for example, simplifies the famous proposition of Newton on Kepler motion, and then later on Feynman gets also interested by this question. So, and then from that time, I start to look in the literature, and I met an incredible historian of science, and I become crazy about the idea to try to teach optics. Let me see that. So it's not very good. Statics, optics, and dynamics, just using compass and ruler. I mean, I exaggerate a little bit, but yes, meaning, and then during this perhaps 10 years, I developed many experiments for school. In school, I mean, from very young people, 10 years old, to the university, using geometry and to discover the law of physics, elementary laws. And today, I'm going to, so by the way, this was a work that I start with Enrique Tirapegui, which leave us last year. And so this is a website that I devoted to this memory, and probably I put all paper published in this teaching activity there. So today I will speak about just one very particular aspect, which is related to optics. And I mean, the idea will be, can we do a simple experiment in school, very simple experiment, to discover the law of refraction without measuring angles, just with compass, and it's even worse, just with a ruler. So, and then I want to show that this is related to question that Ibn Sal in the 10th century in Baghdad did something on refraction. Kepler attempted to do something on refraction, and I will describe the experiment. So, IMSAL. So this is the time, it's Baghdad. And this is my friend Rojdi Rashed, who is a historian of mathematics and physics of the Greek time to the Middle Age. And in particular, in the 90s, he discovered in Tehran and in Damas 2 manuscripts of this scientist, IMSAL, which was known apparently well at the time. And the title of this paper by Rojdi Rashed is A Pioneer in Anaclastics. So anaclastics is a very strange word, which is not used anymore, but is related to the following question. In that case, it's related to lenses, refraction, but it could also apply to reflection. They were looking for the perfect mirror and the perfect lenses, in the sense that, I mean, astigmatic lenses or astigmatic mirror. And you know that for a mirror, the parabola and the ellipse, the parabola, if the source of the light is at infinity, the curve, the parabola is an anaclastic curve for reflection. All rays going from infinity converge to a point which is the focus of the parabola. And this was discovered by Diocles and even probably by the time of Archimedes. I mean, this is called burning mirror. And this, in this year, when this author, IMSAL, published a book on burning mirrors and lenses, burning instruments. But this was a kind of shock for the physics community, because we are all used to think that the law of refraction, I mean, in France, we believe that it's Descartes. In Netherlands, they believe that it's Snell, but probably it's not Snell or Descartes. There are many people. The history of refraction is very, very interesting. And you have a lot of people in the beginning of the 17th century, just after Kepler, like Midorge, Beckmann, Snell, and Descartes. And it's very difficult to know who did what, because they were all discussing with this incredible Mersenne guy who was writing. I mean, this guy was a hub. It was like internet hub, and so you have to read the letters. There is not a very clear history of refraction. Now, so let me, in this diagram here, there is a little drawing here, these two triangles, and this is a law of refraction as IMSAL stated. So it's a postulate, and the postulate of IMSAL is, okay, let's assume here you're underwater, you have a source of light, so a ray starts from here, and the ray is refracted in the air, and this is a path of the light if there is no, I mean, if the recipient was full of water. So this is just any perpendicular to the interface, to the surface of the fluid. And IMSAL states that for a given medium, air, water, glass, the ratio of these two lengths, let's say CH divided by CK, is a constant. So this is exactly the Snell law, because if you look at these two triangles, you get that the sine of this angle is equal to this divided by this. Okay, this is a way that, by the way, when you look later to Kepler, to Ariot also was a very important name, to Snell, and they realize that this ratio appears everywhere. So this is the most obvious fact about refraction, more than the angle. I mean, the ratio of these two things is like this. Now, with this law, I mean, again, this diagram, it's a postulate. I mean, you have to understand that for IMSAL, it's a postulate. So one of the main questions is why all this postulate come from. Then he asks, himself the question of the so-called anaclastic. What is the shape of the lens such that all light coming from a source at infinite distance converge to a point? Something like the parabola, but now for lenses. And he ended up with the following answer. This is an hyperbola. This is an hyperbola, and in addition, he showed that the index of refraction, I mean, the ratio of these two segments is nothing else than the eccentricity of the hyperbola. This was the main result. So the first time hyperbola appear as, let's say, a perfect lens appear in the 10th century, and this IMSAL. So let me show the argument of IMSAL. They are very simple arguments. People of, let's say, 17 years old at school, they can understand that because it's a very, very simple geometrical argument. You don't need to write any equation. You don't need to invoke the Fermat principle. So let's define the hyperbola as a locus of points such that the difference of these two distances is a constant, and you call this constant R. So in the parabola, in the hyperbola, I'm sorry, then you have two numbers. One number is the distance between these 2 points. So we call this 2c traditionally, and the distance and this constant, which is the difference between this segment and this segment. Then what you do is the following. This is a very important. You have these two segments, and you draw the bisector of this angle. Okay, you draw the bisector of this angle, the CT, and you have to show that the bisector of this angle is a tangent of the hyperbola at point C. How do you do that? This is very simple. You have this picture. From G, you take the orthogonal, the perpendicular to the bisectrice. You get a point M as an intersection, and you have a point H as an intersection with this segment. Now, it's obvious that this triangle is isosceles because this is a bisectrice, this is perpendicular, so the bisectrice is the mediatrix. So this is equal to this, CG is equal to CH. So when you express again the definition of the hyperbola, you realize that FH, which is the difference between this and this, so between this and this, is a constant. So FH is a constant in this picture. Then next is very simple. What you have to do is you have to show that this bisector is the tangent. So you take any point C prime on this bisector, and then you do a very little argument and show that this thing is always greater than this plus this. So you always have this inequality. So you cannot be on the hyperbola. And furthermore, when C prime go from one side to the other, you keep this minus. So it means that you're one side of the hyperbola and you touch the hyperbola just in C. This is typical argument used by Apollonius and all these people to show that a curve, to check if a line is tangent to a curve. Then this is quite interesting because this has nothing to do with my demonstration of fraction, but this gives a very, very nice way to define the hyperbola, because now you see, if you draw a circle here with radius r, then you have a way to construct the hyperbola point by point. So, and this circle, by the way, is called the directrix circle. So it's a generalization of the idea of the directrix for a parabola. Parabola is a locus of point equidistant of a point and a line, and the hyperbola is a locus of a point equidistant of a circle and a point G. By the way, if the point G is inside the circle, you describe an ellipse. So it's a very interesting way to, and you see it's very, it's constructive way, because you you draw first the 2 points, you draw this circle, and you say you join G to any point on H, on the circle. Once you have this point, you take the radius FH, you extend, then you take this segment, you take the mediator, and the intersection is a point on the hyperbola, and then it's a tangent, and so on and so forth. Now, the demonstration of IMSAL is very simple. When a ray, now let's assume a ray come from minus infinity here and is refracted here. Then this is a tangent. So take a perpendicular to the tangent. This is GK. And then you have to show that CH divided by CK is a constant for hyperbola. If you do that, you're fine. You have shown that hyperbola is an eclectic curve for the refraction. But this is so obvious because these two triangles are similar. Because they have the same, this angle is equal to this one, and this angle is equal to this. They are similar. So the ratio of these two things is the ratio of this and this. This is 2c, which is a constant, the distance between the foci of the hyperbola, and this is a constant r. So here we have a very simple proof of the fact that hyperbola is an eclectic. Then this book of IMSAL pose a lot of question. How this guy end up with this postulate? This is one of the main question. So, by the way, I forgot to say that the ratio of these two numbers, so is the eccentricity of the hyperbola. So you have hyperbola with, I mean, when you give yourself the eccentricity, you have one family of hyperbola, and then this is something I did with a laser cutter. So all these lengths are hyperbolic up to lengths constructed by the asymptote. So, and this is funny for students because so this length is such that if a ray goes like this, it just follow the side, and then all rays converge to this point. And this is obvious because it's just the called total reflection angle. So, and for water is something like 48.5 degree. So when you go this, you end up like this is arc cosine of 1/n, n being the ratio of the refractive index. Now Kepler. So now why I do that? Because now I want to understand what is a possible way that this IMSAL postulates this ratio. So Kepler in write a book on optics for astronomy, and in particular, you see this thing is ad vitolenium parallelipopema, which means the addition. What this guy Vitelion was a mathematician of the 13th century. He makes the translation without understanding it completely of the famous Alhazen Himmelleitem, great optical guy of the 11th century. And Kepler has this book I don't think he has a book of Alhazen, but he has a book of Vitelion, and he realized that in Vitelium there are a lot of things missing. So this is parallelipopena, seems to mean in Greek that's adding to what Vitelion did. So in Kepler, you start with this discussion with a very complicated picture like this. But you realize that here you see a kind of curve, which is like a hyperbola. And what Kepler I'm going to spend 2 minutes to tell you what this guy is doing, what Kepler is trying to do. And he's using to refraction, he's using the famous table of refraction of Ptolemy. And this is a plot. The black dot are the Ptolemy value of the refraction, and this is exact from the Snell law. So you see, it's not so bad except the last, which is completely crazy because you get this angle is higher than the total refraction angle, which is 48, and this is 50, more than 50. But this is not so bad. So what? So this is a very difficult part of thing to read because you see the picture. The picture is so complicated. So I'm going to simplify this, and first let's forget about yeah. Okay. So you see on this picture, let's assume you have a surface like this. Below you have a refraction index N2, here N1, and then here you have some interface with its tangent. So this is the normal. So here the two angle, I call it psi and theta, which is psi is theta 2 and theta 1 is capital theta. So I have now the refraction law this written this way. So here I introduced something which was used by Ptolemy and the other, which is called the refraction, the deviation of this ray deviate, and this is a deviation. It's just the difference between theta and psi. So it's deviation. So here you see the picture. If you know theta and delta, then you know the tangent. This is what Kepler did. Kepler starts with the value of the delta given by Ptolemy. These are this angle, theta. And then he shows some arbitrary axes. And here, at this point, he draw the line which are such that the angle is psi. And this picture of Kepler is just this one. I don't know if it's clear. So it means that when you have the table of Ptolemy, you have a way to get the tangent of the curve, because the tangent of the curve is this. This is the tangent of the curve. Now let's do the Kepler construction, taking the exact value, and here you get this. Okay, so the construction is the following. You start with, you see all this line here, you start from this point, you take a parallel to this, then you hit the next ray, you do a parallel to this, and this is parallel to this, this is parallel to this, this is parallel to this. It means at each point here, you have the right tangent. What Kepler is doing is solving a differential equation. Kepler is solving a differential equation by, and this was known at the time, later at the time of Descartes, as a problem of inverse tangent. You know the tangent and you want to construct the curve, which is, by the way, just what we call a differential equation. Kepler failed, and you can see it here because here I draw. You remember the property of the hyperbola. The property of hyperbola is the tangent is the bisector of the line which join the two foci. So here you see that when I construct this line such that this is the bisector of this and this, then all things do not converge to a point. And Kepler was a very careful he was very careful guy, and he concluded that this looked like hyperbola, but it's not hyperbola. Based on the table of Ptolemy, but Ptolemy's table is not very accurate, but this is not the problem. The problem you will see very in 1 minute. The problem is that the way he solved this differential equation is by a method which is implicit method. And okay, and then of course, when you have an implicit method to solve an equation, if you decrease the time step or then you will get right results. So this is what I did. So now I take a better table of refraction. I mean, I use the Snell law, and now if you have a better resolution, this is perfect. You get hyperbola. So then Kepler missed the problem, the hyperbola. It says close to hyperbola. I realized that you have a asymptote, but something was wrong in this part. And this is just because he solved the equation with not the right numerical method. Then let me show that. Then my conjecture is the following. Probably Imsal did the same thing. Because when you have realize that when you have the refraction table, you know the tangent. So you try to construct this curve. And perhaps Imsal was more mathematician than oriented people than Kepler. And he said, okay, let's assume that the curve is, the anaclastic curve is hyperbola. And then, of course, you deduce the law of refraction. And then you present your thing the reverse. We know that we sometimes we do something like that. We make a discovery and then we rewrite the way that it's done. Then experiment. Now I have just 3 minutes for the experiment. The experiment is using a ruler without this thing, just a ruler. Is using a little lens. This is a lens that I built with a laser cutter. It's very simple. It's plastic, by the way, it's acrylic. And this is something which allows me to have some reflection. So I am going, and here the experiment I show is one done by a student, and he is using laser. This is not the best way to do it. You can use a very strong punctual light. Now they are available, but let me show this. But first, before I give the results of the experiment, let me do the modeling of the experiment. So now the question is the following. Let's assume I ask the following question. I want to not to reflect, to refract. I want to refract a ray light like this to a given point, and I just know the position of the center of this lens, like L. And I want to know what is the angle I have to put. You see what I mean? At a given point, I am rotating up to the point where I get the focusing on this point. Then this can be reversed, of course, because since in atom, we know that if the light goes from here to here, you have the same path on the other side. This was demonstrated by Alhazen in the 11th century. So in order to answer this question, what is the angle I have to put on this lens so that the refraction occurs on point F? First, I have to write the Snell law for angle theta m psi. This is just a simple trigonometric identity. And then sine and cosine theta are easily related to x and y. And I get this formula. So this answers the question. I give x and y, and f, of course, f is a distance from some origin. And I get this. This is psi is arctangent. So now the experiment consists the following. Assume I know a position of diopter like this, a lens. Then I put next to this lens another one, and I rotate around this point up to the point where I get refraction to point L. So you see, you understand what I'm doing. Then it's very simple to do the computation. You can relate the center, the position of this length to the position of the previous one by a formula like this. But here you see you have a little problem because you get the new position is given in terms of some quantity related to the new position. It's so-called implicit equation. And what is the equation? Then, of course, I have to solve this equation. You remember that when I know the position of the diopter, I can compute the angle. So when you take this, you put it in this thing, you get a horrible equation, you solve with a Newton method, for example, at each step, and you get a curve. And in the limit, I have just one slide. In the limit where the delta is the size of the diopter, is this length here. In the limit where the size goes to 0, you get a differential equation, of course. And this differential equation is this one. You can check that this is a conserved quantity, is a first integral. And this is just the equation of hyperbola. And you get the result. Then this is the numerical results. So this is perfect. You can take now very big diopter because the method is implicit. Since the method is implicit, is much better. And then this is experiment, and I finished. Here, I don't use the student use a laser beam. So the laser comes from this direction, for example. It's refracted here. Some part of the ray is reflected. This is very interesting because here, this reflection here is here and here. If you continue this, it means that this is a line such that this is a bisector of this angle. So when you continue this, you see that the thing is not perfect here, and you see why? Because the guy make a little mistake here. He don't put the second diopter. So you don't use many diopter. You just take one diopter, you draw this, and you change the position. So here you don't have the continuity. As a result, the first thing is not very good, but it works very well in general. So I just say that when you get the idea experimentally that this is a hyperbola, you discover the law of refraction without compass and without measuring angles. And I have many examples of this kind of thing using this very geometrical thing. I finish. I'm sorry for this elementary geometrical thing.
Thank you, Pierre, for this interesting talk. We have -4 questions, -4 minutes for question, very short question.
-4 minutes?
Yes. So is there a very short question? Okay. Pierre, can